Good morning, dear student. In today's lecture, we are very much interested in the important heterogeneous catalysis, that is ziegler-natta catalysis, the ziegler-natta polymerization of olefins. So, if you consider this ziegler-natta catalyst, why this ziegler-natta is important in the polymerization of olefins? So before discussing their importance, let's discuss some important points regarding to the history of this ziegler-natta polymerization of olefins. So if you consider, the first important point is that the polyalkenes are among the most common polyalkenes are among the most common and useful class of synthetic polymer. So polyalkenes are the most common and useful class of synthetic polymer. Second, the original ICL process. So the old process which is used for this polymer, that is ICL process. The original ICL process which is used for production of polyalkenes. The original ICL process which is used for production of polyalkenes involve polyalkenes involve the use of high temperature and pressure. So before discussing this ziegler-natta polymerization of olefins, you should know this point, that the polyalkenes are the most common and useful class of the synthetic polymers. The ICL process which is used for formation of polyalkenes involve the use of high temperatures and pressure, and it is called thermal polymerization. This ICL process, it is called as thermal polymerization. Thermal polymerization, because they require high temperature and pressure. That is, if you consider the ethylene, n molecules of ethylene in presence of 200 degrees Celsius and 1000 atmospheric pressure, they are converted into polyethylene, that is CH2. So the alkenes, that is your ethylene, is converted into polyethylene. So this process required very high temperature and pressure, and therefore this process is called thermal polymerization. This process is called thermal polymerization. The next important point is that in 1950, that is in 1950, that is 1950, in 1950, uh, Ziegler, that is Carl Ziegler, it is from Germany. Carl Ziegler of Germany developed a catalyst of ethylene polymerization. So in 1950, Carl Ziegler in Germany, from Germany, a catalyst catalyst for ethylene polymerization. Ethylene polymerization. Develop catalyst for ethylene polymerization. And later on, if you consider the history, later on, the natta of Italy, utilize this type of catalyst, utilize this type of catalyst this type of catalyst for specific stereospecific, not specific, for specific stereospecific polymerization of propene. Polymerization of propene. Polymerization of propene. So, in 1915, Carl Ziegler from Germany developed the catalyst for ethylene polymerization, and later on, Natta of Italy utilizes this type of catalyst for stereospecific polymerization of propene, okay, and other alkenes, propenes and other alkenes. This Ziegler and Natta both receive or awarded. This Ziegler and Natta are awarded by Nobel Prize, awarded by Nobel Prize in chemistry. They are awarded the Nobel Prize in chemistry in 1963 for this one of the great discovery in organometallic chemistry. And nowadays, vast quantities of this polyethylene and polypropylene are produced by Ziegler-Natta catalyst. So they gained the Nobel Prize in chemistry in 1963 for this one of the great discoveries of organometallic chemistry. And this catalyst, it is used for various type of production such as polyethylene and polypropylene by using this Ziegler-Natta catalyst. So let's discuss about this catalyst. That is, the Ziegler-Natta catalyst is prepared in situ. This catalyst is prepared in situ by mixing or by treatment of titanium tetrachloride TiCl4 with triethyl aluminum. Triethyl aluminum. That is triethyl aluminum. That is Al(C2H5) thrice. So the catalyst, it is prepared by the reaction of titanium tetrachloride with triethyl aluminum in hydrocarbon solvent. In hydrocarbon as a solvent such as N-heftane. So this TiCl4 and triethyl aluminum react together to give polymeric insoluble and fibrous form of TiCl4. So after mixing this TiCl4 and triethyl aluminum gives polymeric insoluble and fibrous form of TiCl4. Fibrous forms of TiCl4, which is used in the form of fine powder. This catalyst is heterogeneous catalyst. Okay, this Ziegler-Natta catalyst is heterogeneous catalyst. So you should keep in mind the difference between homogeneous catalysis. So whatever the process we discussed earlier, that is hydroformylation, Wacker process, then Monsanto acetic acid synthesis. So whatever the catalyst which is used, they are homogeneous catalyst. But this Ziegler-Natta catalyst is your heterogeneous catalyst. So you should first find out the difference between the homogeneous and heterogeneous catalyst. So it is prepared by the treatment of TiCl4 with triethyl aluminum in hydrocarbons, and after that treatment we get a polymeric insoluble and fibrous forms of this TiCl4. Again, the next important point is that this Ziegler-Natta catalyst can be used for polymerization of ethylenes and other alkenes under ambient conditions. So they used under ambient condition ambient condition of temperature and pressure. Ambient condition of temperature and pressure, that is uh, the temperature, that is room temperature, and the pressure is 1 atmosphere. So if you consider the reaction, that is NCS2 in presence of this catalyst, that is TiCl4 plus triethyl aluminum, TiCl4 in presence of triethyl aluminum. So at a temperature that is 25 degrees Celsius and pressure is 1 atmosphere, and we get the product, that is CS2. So we get the polyethylene. So for this Ziegler-Natta catalyst, we required a room temperature and the pressure, that is 1 atmosphere. So it is very less as compared to the ICL process, in which we required the temperature, that is 200 degrees Celsius, and the pressure, that is 1000 atmospheric pressure. So this is the uh, importance of this Ziegler-Natta catalyst in the polymerization of these olefins. So we required the room temperature and the pressure is 1 atmospheric pressure. So let's discuss the remaining points regarding to this Ziegler-Natta catalyst. If we consider a large amount of work has been directed to how this catalyst is work. So there is a lot of study regarding to this lot of study are going on this catalyst, so how this catalyst is work. So we will discuss some important we will discuss the mechanism of this Ziegler-Natta catalyst. What are the different steps? So first, if you consider the TiCl4 is there, this is your Cl, and this titanium has having a vacant site. So this is your vacant coordination site. When this triethyl aluminum, that is ALET thrice, it will react with this TiCl4, then what you get, one of the chlorine atom, it is replaced by the ethyl group from triethyl aluminum. So whenever this TiCl4 it is react with your triethyl aluminum, one of the chlorine is replaced by the ethyl group of this triethyl aluminum, and we get this, that is TiCS2CH3Cl, and then this is your Cl, this is your vacant site, and this is also the vacant site is there. So we get this, that is TiCl3Et. So we get TiCl3Et, and we get this, that is aluminum Et twice Cl. So in the first step of this mechanism, TiCl4 react with your triethyl aluminum, and there is a replacement of one chlorine from titanium by the ethyl of this triethyl aluminum. In the second step, the titanium atom having a vacant coordination site, and a molecule of ethylene is coordinated to titanium atom through this vacant coordination site. So the first step is the replacement of one of the chloride or chlorine by your ethylene, and second is the coordination of olefins, that is carbon carbon double bond, coordination of olefins, that is it having a vacant site, so there is a coordination of olefins. So what you get here, so this is the complex, this is your CH2 CH3, this is chlorine, this is your chlorine is there, and this is the vacant site is there, and this alkenes, that is carbon carbon double bond, it will interact with your, it will forms the bond with titanium, because this titanium having a vacant coordination site, and we get this, that is titanium CH2 CH3. Here the alkene is coordinated, its safety is 2, and then there is a chlorine is there, and having vacant site is also there. Okay, so this is the second step. So in the first step, replacement of this chlorine by the ethyl group. In the second step, coordination of olefins to the vacant site. Coordination of olefins to the vacant site. In the third steps, so let's discuss the third step, that is after coordination of alkenes to this titanium. In the third step, the coordinated ethylene molecules is inserted into titanium carbon bond via 4 center transition state, and this process is known as cis insertion. So there is a chances of 1-2 insertion. So this is the process, that is Ti CH2 CH3, then this is your chlorine, and then this is also your chlorine, and this is your CH2 double bond CH2, this is your CH2 double bond CH2. So we know that whenever there is a coordinated alkenes which is attached to the metal atom, and one sigma donor ligand is present, then there is a chances of 1-2 insertion reaction. So what is this 1-2 insertion? We are very much familiar with this 1-2 insertion reaction. It is whenever there is a coordinated alkene and so the sigma donor ligand is present, such as hydrogen or alkyl group is present, then there is a chances of 1-2 insertion reaction. So this 1-2 insertion reaction results into the formation of a new bond, that is this ethyl group is shift from this titanium atom to this carbon number 2. So let us consider this carbon number 1, this carbon number 2. So this group is shifted on to this carbon, and the hepticity 2 is converted into hepticity 1. So in this case hepticity is 2 of these alkenes. So what happened after 1-2 insertion, the hepticity 2 is converted into 1, and this bond of this titanium carbon bond is break, and we get this, that is we get titanium, this is your chlorine, this is your CH2 CH2, and this ethyl group is attached to this carbon number second, this is 1 CH2 CH3, this is your chlorine, this is your chlorine, and there is again formation of vacant site, there is a formation of vacant site. So this is happened due to this 1-2 insertion reaction, that is hepticity of 2 is converted into hepticity 1. So only one carbon is attached to the metal atom. So in this case both carbons are attached to this metal atom. This is a 1-2 insertion reaction. So whenever there is a 1-2 insertion, hepticity is decreases by 1 unit, and the ethyl is transferred from this titanium atom to this carbon atom, carbon number 2, and there is a formation of vacant site. So this complex can be written as in this way, that is we can write this as titanium, this is your CH2 CH2, and this group it is considered as ET, that is ethyl group. Again there is a chlorine chlorine chlorine, and there is a vacant site. So for our convenient we can replace, we can write this structure as like this for our mechanism purpose. Again there is a vacant site, and the coordinated alkenes, the olefins is interact with this vacant coordination site. So let's discuss the next step. So there is a polymerization. So in the first step, the replacement of the chloride by ethyl group, then the coordination of olefins to the TiCl3 ET complex, and then after that there is a 1-2 insertion. After 1-2 insertion, the hepticity 2 is converted into 1, and there is a generation of another vacant site. Again the alkene molecule is interact with your vacant site. So what you get here, so the third is again there is alkene molecule interact with vacant site, that is Ti CH2 CH2 ET. After coordination of first alkene we get this Cl Cl, and this is your vacant site, so alkene. So in this case we can directly write here the alkene is coordinated, alkene is coordinated to this. So this is your vacant site, and the reaction with carbon double bonds. So what you get here, so Ti ch2 ch2 et. Here chlorine is there, coordinated alkene is there, then chlorine, chlorine, and this is, so we get this. Again, this species undergo 1,2 insertion reaction. So this species undergo 1,2 insertion reaction, and what you get finally, we get this, that is Ti Cl Cl with formation of vacant site. This is chlorine, and we get here, so this group is there, that is two more carbon is attached to this carbon. So total there is a three carbon is there. So after that we get five carbon. So this is your ch2 ch2, then ch2 ch2 et is there. So it is 1,2 insertion, same like this, 1 2, the heptacity 2 is converted into 1, and the group ch2 ch2 et is transferred to carbon number second. So this is 1,2 insertion, and we get this with vacant site, and the process is continued, with alkenes, that is ch2 double bond ch2. So this is the mechanism. This is the mechanism of this Ziegler-Natta polymerization. And the last step, that is, so how to stop this polymerization? The chain termination. The chain termination. The chain termination can be takes place. Chain termination can be takes place by beta hydride elimination. Beta hydride elimination can be takes place by beta hydride elimination or hydrogenation reaction. So this is the complex, that is Ti Cl, Cl is there, and this is your ch2 R group is there. So with respect to, this is your alpha, this is your beta hydrogen. So beta hydride elimination we already discussed it. So the hydrogenation transfer from beta position to this metal atom, Cl, and we get this, that is ch2 double bond chr, that is termination of this polymerization by beta hydride elimination. Or second, it undergo hydrogenation reaction, the reaction with H2. So same reactant is there, reaction with H2 to give titanium, hydrogen, Cl with elimination of RCH2 CH3, RCH2 CH3. So this is all about the mechanism of this Ziegler-Natta polymerization. So this is all about the Ziegler-Natta polymerization for olefins. So at least you should know the catalyst and the mechanism of this Ziegler-Natta polymerizations of olefins. You should know the mechanism of this Ziegler-Natta polymerization of olefins. Whatever the applications of this Ziegler-Natta catalyst, you should find out this application and write the use of this Ziegler-Natta catalyst in your notebook. Okay, so this is all about Ziegler-Natta polymerization of olefins. In the next lecture we discuss the remaining points of our chapter. Thank you.